Today we're going to talk about electromagnetic induction. Induction is the generation of electromagnetic force, or EMF, and thus a current by means of electromagnetic fields. This is the intersection between magnetism and electricity. For this to occur, a conductor must always be moving through the electromagnetic field for induction to occur. If the conduction is motionless, then no current will occur. This is an example of what's known as Faraday's apparatus. Faraday's apparatus is an apparatus that was used to demonstrate that an electromagnetic field could produce a current. A change in the field produced by a coil induced an electromagnetic force and hence a current in the bottom coil. You can see that in the middle here are two coils, one of which has an induced field and the other has an induced current, which is measured by the galvanometer. When the switch is opened and closed, the galvanometer registers currents in the opposite direction. No current flows when the switch either remains opened or closed. The movement of a magnet relative to the coil produces the electromagnetic force as shown. The same EMFs are produced if the coil is moved relative to the magnet. So the magnet can be moving or the coil can be moving. The greater the speed, the greater the induced EMF. And the EMF is zero when there is no motion. Now, if you look at A, in A, the magnet is moved up into the coil, and you have an induced field or an induced current that travels clockwise and deflects the galvanometer to the right. When you move the magnet in the opposite direction, the induced current is in the opposite direction, and the galvanometer is deflected to the left. Again, if you move back up, but you change the poles, notice that in C, the poles north and south are changed, then the induced field is in the opposite direction and is the same as B, even though the motion is in the opposite direction, it's the same because the poles are reversed. And then D and A are the same, even though the poles are reversed. And if the two are stationary, then there is no field. And there is no current induced. Now, the other way that you can do this is to rotate a coil through an electromagnetic field and produce a current that way. And this is actually how most generators work. A generator uses kinetic energy to rotate a conductive material or a coil through a magnetic field, and this in turn converts to electric energy. The generator is essentially the opposite of an electric motor that we studied in the last chapter. The generator is the use of kinetic energy to generate an electrical current. The electrical motor is the use of electrical current to generate kinetic energy. Now, the way that we calculate electromagnetic induction is shown here. The calculation is based on the measurement of something known as magnetic flux. And magnetic flux is the product of the magnetic field times the area through which that field passes. Now, when you're measuring magnetic flux, the area has to be perpendicular to the magnetic flux or field. Therefore, a factor of sine theta, which calculates the perpendicular component of the magnetic field, is taken into account. The flux is related to the induction, and any change in flux is what induces the electromagnetic or the EMF, the electromagnetic force. So when you look at the flux, you see that that is equal, flux, which is psi, is equal to the electromagnetic field times the area through which it passes times cosine theta. Now, if the field is perpendicular to the area, then cosine theta is 1. Faraday's law of induction states that the induced EMF is equal to the number of coils multiplied by the change in flux over time. So EMF is equal to N, which is the number of coils, times the change in flux. This is what's caused by motion over time. The result is negative because the induced current is opposite to the change in flux. And this is known as Lenz's law. When this bar magnet is thrust into the coil, the strength of the magnetic field increases in the coil. The current induced in the coil creates another field in the opposite direction of the bar's magnetic to oppose the increase. This is one way in which Lenz's law is in effect. The induced field by the current that's induced is opposite to the change in flux. B and C are the other two situations. You can use the right-hand rule number 2 in order to show this, that the induced field in the coil will be in the opposite direction of the change in flux by the magnetic field. And you can stop the tape at this time and look at, or stop the video at this time and try this out to see if you can figure out exactly what it's talking about. So the change in flux is in the direction into the coil. So the induced field is in the opposite direction. And so that's what's shown in B and C. Take a few minutes and stop the video if you need to in order to get this visualized in your mind. This is one of the hardest parts of understanding this whole chapter. So in order to do these problems, first of all, you need to make a sketch to visualize the directions that are occurring in terms of the direction of the change in flux, the induced current that results from that change in flux, and the resulting field from that current will be opposite. And if it's not, then you have the direction of the current in the wrong direction. You determine the direction of the field, then whether the flux is increasing or decreasing. The direction of the induced magnetic field will always be opposite to the change in flux. Using the right-hand rule, you can use that opposite to infer the direction of the current needed to create that induced field. You can represent this as an EMF from positive to negative. So let's take a look at a couple problems now. Okay, the first problem states, suppose that a 50-turn coil lies in the plane of the page of this book in a uniform magnetic field that's directed into the page. The coil originally has an area of 0.5 and it's stretched to an area of 0 in 0.1 seconds. So the flux is decreasing and its direction is into the page and it's decreasing. Okay, so that's something you have to keep in mind. So what is the direction and magnitude of the induced EMF if the uniform magnetic field has a strength of 1.5 Tesla? Well, let's do the calculation first. That's actually the easiest part here. So first of all, we said that E is equal to N times the change in flux over the change in time. And that's going to be equal to N times the field times the change in area, sorry about my handwriting here, over the change in time. This is actually a negative, this is a negative, equals 50 turns times 1.5 is the and the change in area is from 0.25 to 0, and that all occurs over 1.1 seconds. And so if we do this, we get 187.5 volts, okay? Now, according to the problem, it's in the plane of the page, the field is directed into the page, and it's decreasing, okay? So the induced has to be coming out of the page, and so it would have to, if you use the right-hand rule, but it's decreasing, okay? So if it was increasing, it would be, according to the right-hand rule, it would be counterclockwise. Your fingers, if you take them counterclockwise, the field would be coming out. But since it's decreasing, it's in the opposite direction, and so it's clockwise. Let's look at the second problem here. Second problem states that an MRI technician moves his hand in the region of a very low magnetic field strength into the MRI scanner. So he starts at a low field into an MRI scanner, which has a very powerful magnet, 2 Tesla magnet. His fingers are pointing in the direction of the field, so that means the ring is perpendicular to the field. Find the average EMF induced in his wedding ring given the diameter of 2.2 centimeters, assuming it takes 0.25 seconds for this to occur. Okay, on this situation, it's the same formula, but instead of 50, you have a ring has 1 loop, the field is 2 Teslas, and now the area change is going to be pi times the diameter of the ring squared. And the diameter of the ring here, I'm sorry, the radius of the ring squared. The diameter of the ring is 2.2 centimeters, so the radius of the ring is 1.1 centimeters, or 0.011 meters. And this all occurs in 0.25 seconds. Got to work on my handwriting here. Sorry about that. So this is 1 times 2 times pi times 0.011 over 0.25. And that's 3.04 times 10 to the minus 3. This is squared, by the way. Sorry about that. Volts, or 3.04 millivolts. Now the second question here is, the second type of problem that can be encountered is something called motional EMF. And motional EMF occurs when this rod moves onto these 2 parallel rods and is attached by a connector. Motional EMF is measured by the formula given here. It's the field times the length of the rod times the velocity of the rod. The length and velocity of the rod are related to the change in area. And if it's moving from right to left, the field's getting smaller, the flux is getting smaller. If it's moving from left to right, it's getting bigger. And therefore, in one instance, the current is in one direction. In another instance, it's in the opposite direction. And when it's moving to the right, so that the flux is getting bigger, then the induced current is counterclockwise. Again, according to, you can see the right-hand rule here shows the field, the velocity, and therefore the force is up. And so that means the current is moving this way. And you can also see by the left-hand rule, or right-hand rule 2, that this is in the opposite direction. This induces a field in the opposite direction to the one that's present. And Lenz's law, and that's Lenz's law, in the fact that this induced current, this current, causes a field that's exactly the opposite direction of the one that's being measured. So here's an example of motional EMF, and this is a problem that's actually, if you look in your book, this problem is in your book, and it's a way of generating electricity using a very long tether and a satellite. You use this motional EMF to generate electrical power by passing this very long tether through the magnetic field of the Earth. So if you have a shuttle that's traveling at 7.8 kilometers per second, has a 20 kilometer tether in the Earth's magnetic field, and the Earth's magnetic field is 5 times 10 to the minus 7 Teslas, as shown here, and the circuit is then completed, what is the induced EMF? If you look on page 818 in your book, you'll find the solution to this. It's very simple. The induced EMF is equal to the field times the length of the tether in meters times the speed in meters per second. If you do the calculation here, and between the slide and here, the magnetic field of the Earth is different. One says 10 to the minus 5, one says 10 to the minus 7. If you use the 10 to the minus 5 number, you get 7.8 times 10 to the 3, or 7,800 volts.